So the first part of my lecture was a discussion of the Hubbard model on the honeycomb lattice, which at half filling, which shows a paradigmic example of a quantum phase transition from a semi-metal to an insulator. And in the insulator, at the same time, there's antiferromagnetic order. So here, you can really think of the insulator as arising from a broken symmetry. So there's a broken symmetry in the antiferromagnet, and that opens a gap in the electronic excitation spectrum. So, kind of two things happen at the same point. There's a broken symmetry, and at the same time, you open a gap when you go from a semi-metal to an insulator. All right. So theoretically, I would say this is very well understood, at least at zero temperature. What happens at finite temperature, there's still some very interesting open questions on how you actually compute the conductivity, especially near this quantum phase transition. So that's sort of what I addressed last time. Okay, so where I want to go today in this lecture is to go to the case, again, of something like this, some kind of transition, but we want a transition not from a semi-metal. We want to make this an actual metal. So in an actual metal, okay, the simplest way you could do it in graphene, you just change the density. So if this was your Fermi level up here, then you'd have a whole circle at which you have zero energy excitations. And so it'd be a property of a Fermi surface. So we could do that in graphene, but I'll go to the case of the square lattice because experimentally, a Fermi surface with magnetic order is something that's relevant to many, many compounds. Of course, also to the cuprates to some extent, but more relevant to things like the pnictides and some of the nickelates, and there's many correlated electron materials, many of which also go superconducting. We really have to think of the analog of this transition in the presence of a Fermi surface, not just a Fermi point, but a whole surface or a line where you have zero energy excitations. Okay, so that's where I want to go today, and try to then understand eventually something about the strange metal behavior in the cuprates, which has some similarities and some differences from what happens for graphene. Okay, so on the way there, we discussed last time the SYK model, which seems very, very far away from all of these considerations. It has electrons in random positions, and then they interact with random interactions. But it has the property, one nice property, is that the density of the electrons, the density of the purple fermions, is arbitrary. It doesn't have to be half-filling. It can be anything. Not too far from half-filling, but there's a whole range of densities where you have the same behavior, independent of density. And that seems a good thing. Again, even with graphene in principle, so there's a special behavior at half-filling. Half-filling is something really special, and we really use that property in our discussion. Yeah, so if your Fermi level is here, that's a very, very special point. But once you move away, then it doesn't matter if it's here or here or here. It's basically the same, okay? So that's the feature we want in our theory, where the density is not at any commensurate value, because that's what you see in experiments. So that's a feature the SYK model builds in. You put electrons of any density, and remarkably, independent of the strength of the interactions and independent of the density, you always find at low temperatures this Planckian scaling. The electron spectral density has this form where the line width is basically K temperature. And there's also an overall amplitude, which is 1 over square root of omega, or 1 over square root of temperature. So this, in the end, is something you can work out, just a few equations. It took a while for us to sort out the structure of the equations, but now you can just explain everything in a few lines, and hopefully I did most of it last time. Okay, so, so today I want to first begin by another model, which is called the Yukawa SYK model, which appeared in many disconnected papers for different reasons. But the form I'm going to discuss now is due to Estelis and Schmalian here in 2019. So what is this model? So now this model is sort of like we're going to do the baby version of what we did with graphene. With graphene, you had a Hubbard model of interacting electrons. And then we found it was useful to write it as a model of electrons interacting with a scalar field. We introduced a scalar field by some transformation. And then we wrote a theory of coupled fermions and bosons. So let's do that here. I think if you look at the Schmalian paper, they just think in terms of this scalar field is just a phonon. So imagine you have some phonon, lattice vibration, and all the phonons have the same frequency, omega 0. So you just have a whole bunch of phonons with exactly the same frequency. And then they interact with these electrons, which are in a flat band. They're all have the same energy. So you have Einstein phonons interacting with the flat band. Okay, so there's no dispersion for the phonons or for the flat band. And then there's a coupling. This is the electron-phonon coupling. And there's a coupling constant G. Okay, so this model is simple enough that it's sometimes, I think it's called the Holstein model, when G is just a constant. But we're going to allow G to vary, and in fact, we're going to, in the spirit of SYK, take this G to be a random function of its indices. So you have a 3-index random tensor, G, I, J, L, and this is just some random function. Okay, so that's the model. You know, and you are asked to solve it. And just like the SYK model, you can solve it in the large n limit, where n goes to infinity. And then you can also put it on a computer. You can do Monte Carlo simulations for any n you choose. And that's also been done, and everything really hangs together very nicely. So, so how do you proceed? So this is the Yukawa phonons interacting with a flat band. Well, you can do the same tricks we did for SYK. You average over the couplings, then you get some action, and you look at the saddle point equation for the action, which are here.
I have a question. So is it natural to think that it's really dependent on all of these indices, I, J, and K? I mean, physically, when you think about it. Your G is dependent on I, J, and K. Is it natural to think that it depends on all of these indices?
No, it's not natural. Just like the SYK model, it's not natural at all. Well, I mean, there will be some dependent. If you actually had a flat band, then all the states are the same energy, and then you couple it to a phonon. There will be some. There won't be the coupling constant won't be independent of the band indices. This is something called quantum geometry these days. Mm-hmm. There are some complicated wave functions for the flat band. And those come into the nature of the electron-phonon coupling. There's lots of papers on this kind of thing in TBG these days, where you have flat bands, and then there's still, nevertheless, the wave function. So it's some complicated function. Hasn't have any, depends on exactly what the flat band is. So we just say, okay, it's a random number. That's all. And it's probably true for this model that if you took not exactly a random number, but a pseudo-random number, where it's some function which is looking kind of messy, it will probably have the same properties. Yeah, at least for this model, yeah. Yeah. This is the electron psi. This is the electron, yeah. phonon. That's the phonon displacement. This is just a harmonic oscillator. This is the momentum of the oscillator. This is the pi is the momentum of the oscillator. This is the displacement of the oscillator. It's just a harmonic oscillator. Yeah. So these are what are called Einstein phonons. Basically, I don't know. And if all the phonons have the same frequency, we call it an Einstein phonon. Probably there was some model that Einstein wrote down sometime. Yeah. Yeah, actually, it's not the famous Einstein. It's a different Einstein. I think it's a different Einstein. Is it Ted Einstein? Yes. I think so. Okay, somebody can correct me. Ask ChatGPT. He did? Okay, maybe you're right. Okay, maybe it's some other. Okay, but anyway, okay, great questions. Yeah, but so it's not unreasonable, actually. I correct myself. There could be this quantum geometry of the flat band that will give you some strange function. And unless it has some very special value, yes? Yes, it's the famous. Yes, thank you. Okay, thank you. All right. Yeah. Well, thank you. Okay. So this problem with G, Ij, we just do the simple thing of making G, Ij a random function. Then you can solve it. And the whole steps are exactly the same for that we did for the SYK model, so I won't go through it. And this is the answer. So now you have two Green's function. G is the Green's function of the fermion and the self-energy, just like in SYK. And D is the Green's function for the phonon with the self-energy pi, okay? And then the self-energies are functions of the Green's function. And here it is. So this is, I can draw a picture of it, which in fact, maybe I have in this next slide. No, I don't have a picture, sorry. So the picture is simply you have an electron comes along. This is psi. And then it emits a phonon, which is the dashed line. And then it comes back. So this is the G, the random G here, and the random G here. And that's it. So this little graph is exactly sigma is D times G. Okay? So this thing is G, and that's D. And this is sigma. Okay, and the other graph, which is D, and our pi, the self-energy of the phonon, is the phonon goes along. No, sorry. How do I do it? Yeah, the phonon goes along, and then you get a particle-hole pair. You get an electron like this. And this is G, and this is G. And so now pi is GG, which is that. That's it. Okay, so that's it. It looks very similar, but you have to remember, where does the information come in that, one is a boson, the other is a fermion. Well, it comes in, you have to put that information in. It's really very important. It comes in from the structure of the spectral density. So if you write any Green's function, G of omega, if you write it in a spectral form, or Z, you can always write any Green's function in this way. There's some spectral density here, rho, of omega minus Z, where this is a real function on the real axis, minus infinity to infinity. This is a real function, rho, and Z is a complex number. So this is how you always define the Green's function. And this is the spectral representation, and this is a spectral density for which there's a Lehmann spectral representation. So there are certain constraints on the Lehmann spectral representation. which are different for bosons and fermions, and that's absolutely the thing you have to keep track of. That's, in fact, the non-trivial part of all of this, is to make sure that all the spectral densities work sense, so that the final solution you're finding is a solution for a unitary system with a well-defined Hamiltonian. So it's easy to lose sight of that, but that was really the hard part of solving these equations. Anyway, so you do exactly what I did on the board for the SYK model, and that was done in these papers in this case. So again, you make an assumption that there's some power law in the G, and then you can deduce the power law in D, and then you get some complicated equation for delta. Now, yesterday I had a very simple equation. It was something like 3 alpha minus 1 equals 1 minus alpha. Here it turns out to be a bit more complicated. And for the case with the number of bosons and fermions, that equation turns out to be this. And then there's a solution. Okay. So the exponent was 1/2 last time, but here it's some irrational number. Okay, so in the end, so it's a little bit more complicated, but the structure is very similar to SYK. You have no quasi-particles, you have some power law spectral density. You also have the time reparameterization symmetry, because in the low energy limit, again, this omega and that omega squared just drops out. So that means there is always a time reparameterization symmetry. And for the experts, there's also then the Schwarzschild dynamics and the mapping to black hole physics. So all of that works for this model too. And in fact, if you take, so that's the quantum critical states. It's independent of the coupling. There's always a quantum critical state. And then if you take the spin-a-half version of it, there's even a superconductor. So that's a very beautiful thing. You're getting finally, over some regime, some strange metal coming into a superconductor. Okay, so I won't talk about the superconductivity today, but anyway. Okay, so that's really all I have to say about the Yukawa SYK model. It's a toy model in a flat band. So the rest of this talk will be what are we going to do? So I'll motivate it now, but maybe I can even write what I want to do on the board so that you see the connection to this model. So I'm now what I'm going to do in 2 minutes is start from some physical model that you might find quite reasonable for the cuprates. And after lots of manipulation, I'm going to argue, based upon many years of work and lots of calculations by many people, that the way we should address the physics of that model is a generalization of this Yukawa SYK model.
So I have a question. Maybe I got confused. So there is a G there, right? And then the delta is nothing to do with G.
Delta is an exponent. G, that's right. The delta is the same.
But your phase diagram was dependent on the G, right?
There are at finite temperature. There's some crossovers and so on. Yeah, you can read these papers for the details. But the value of delta doesn't depend on G, but there could be various amplitudes. There's a squiggle. There's a coefficient here. That will depend on G. The exponent does not. The exponent is. What the exponent depends upon is actually the ratio. So if you have a system, I took the simple case. If you have a system of n phonons coupled to m fermions, then delta depends on m over n. It depends on the ratio of the number of fermions to bosons. This is the answer for m equals n, but it depends on m over. That's the only thing it depends on. You can find the full equation in this paper of Estellis and Schmalian. Yeah. Yes, again, there's the same argument. There is no other solution, and that's also been checked numerically. So this model is just always a quantum critical model.
Okay.
Yeah.
Thank you.
Now, of course, the natural question, which the answer is no, maybe that that very special feature is a consequence of having a flat band here and an Einstein phonon here. Neither of those two assumptions are realistic. And the answer is, yeah, it is an artifact. And we're going to try to fix that now and see what we get. And if I don't get there, what we get is something that looks really like the experiment. So that's what we were pretty excited about. Okay, so just let me put the model up there in its own glory. And now let me tell you what we're going to do. So it's a somewhat long argument. It took us several years of dead ends to get here. So I'll go through that argument in some short ways shortly, but let me actually give you where we're going. All right, so we're going to look at a model, and I'll write it as a field theory rather than a Hamiltonian. So the first term is just fermions in a flat band. That's bad. So let's not put them in a flat band. We're going to have them some dispersion for the fermions, Ek. So it'll be psi dagger, psi. Okay, so this is, well, if you want to see a Hamiltonian, let me stick to a Hamiltonian. So you should be able to follow this even if I don't. Yeah, the Hamiltonian would be sum on K, some dispersion, psi dagger K, psi K. So in terms, we're going to take a two-dimensional K, Kx, Ky, and there'll be a line here, which is called the Fermi surface. Okay, and this Fermi surface will be is the line where Ek equals 0. Okay. All right. So that's something we're going to add. That you absolutely have to add that. Nobody's going to, no condensed matter theory is going to believe what you're doing unless you have a Fermi surface. Every material has it. Okay. Then the phonons, of course, you've got to give them a dispersion. But we're going to now think of phi as our order parameter, just like in the honeycomb lattice. So we're going to add some grad phi squared. We're going to take a Landau-Ginzburg theory plus S phi squared plus some U phi to the 4th. Okay? So that's also very realistic. There's some broken symmetry, and in fact, for the cuprates, this is a Higgs field, but all right. That's the simpler case, there's some broken symmetry, just like there was on the honeycomb lattice. And this is the order parameter. It's not a phonon, it's some order parameter. And finally, there's the Yukawa coupling. Now, there's no real, so this is all in, in real space. This is D2x. And then finally, there's the Yukawa coupling. So that I also write in real space, D2x. You'll see why I'm doing this here. G times phi, psi dagger, psi. There are some indices, but I'm dropping them. And the indices are different depending upon which problem you're addressing. But it turns out the final behavior doesn't matter so much. Okay, so this is just some more reasonable form of the Yukawa SYK model, where you have a scalar field coupled with a coupling G to phi. Okay, so now what happens in the real world is you do have this randomness, but the randomness is a function of space. It's not really a function of some, yes?
So here we're considering the phonons as basically an effective theory. Like
this is not a phonon, so.
Yeah, so my question was related to that. Like, is it possible to include like the lattice symmetries into this?
Absolutely, all of that you can include, but in fact, none of it matters.
Right, it doesn't make a
and
difference.
the reason doesn't matter because of what I'm going to say next. A real system always has impurities, and it turns out for this problem, the impurities are really important because without it, you don't even get a strange metal, but that'll take me a long route. So you have to put in some impurities. So the way people normally put in impurities, which we will also do, is you put in some potential V of X that acts on the fermions. Okay, so this thing is a random function of position. This is what you do in the theory of disordered metals. So V of X prime, and disorder average is some V squared times delta of X minus X prime. Okay. So if you just took this and this with some Hubbard interaction or something, then you get the theory of disordered metals, which books have been written. There's a beautiful review article on Lee and Ramakrishnan, theory of disordered metals. There's all kinds of corrections from localization and anti-localization and so on, all well understood, experimentally checked, and so on. And that comes from just really thinking more carefully about this. But we are interested in the case where somehow the phi field, as written, the phi field is not critical. But when S, it'll turn out we'll need to tune something. Unlike the bare Yukawa SYK model, we need to tune it. Then we have to worry about disorder near the critical point. And this is the way people normally thought you should. But what we are going to do is also make the Yukawa coupling. This turned out to be the key step that took us several years to realize. You want to make the Yukawa coupling also a random function, have a component that's a random function of space. All right, so that's the model. This is still a very complicated field theory. We don't know how to solve this, although now there's been some very beautiful Monte Carlo work by Avishkar Patel and Peter Luntz, who really studied exactly this model, some variation of it. But if we want to solve it analytically, which is what I'm going to do here, we still need to take the large N limit. Okay, so we're going to take a large N limit by just putting flavor indices everywhere. Just because that worked for the SYK model. So let's just take this theory, put additional flavor indices, and take the large N limit, make everything random in flavor, and take the large N limit with no justification whatsoever. We're just going to do that while including all of this spatial structure. The physics is in all the spatial structure. The large N limit is simply something to make us feel better that there's some limit where this is exact. But we're interested in the case n equals 1. Yeah.
Maybe a comment of clarification. I'm not bothered by many flavors and large N. I mean, everybody needs to do that at a certain point, right? So otherwise, we cannot solve anything. I want to be provocative. I could have skipped all the SYK part and the Yukawa SYK part, technically, and could landed on this model, right? Because if I get it right, you are throwing away all the beauty of the disorder coupling of SYK that is all well connected. Now this feature is lost, and I could have written this model after your lecture on graphene.
Well, I probably did write it. So many people wrote it, this kind of model. There's something called the Hertz theory. Hertz was the first to write it down. And then many people wrote it. It's discussed in my quantum phase transition book, which was published in 1999, and so on, with one exception. None of those treatments, until the recent work, had this random coupling constant. They didn't have this.
Okay.
Okay. And we were inspired to put this in.
By Yukawa SYK,
yes.
of course. Of course.
Yes.
Okay.
And then once it's there, they start to realize it's actually very physically correct. It should be there. And for whatever reason, so it's different. And this could have been solved without anybody knowing about SYK, but it wasn't.
Okay.
I mean, if I could spend 3 hours talking about all the wrong routes we took. So it looks kind of obvious. Why didn't somebody think of this? Well, It took sorry. All right, so now I'm going to do what Yamir said. I'm going to just start from a microscopic model and eventually end up. And then, okay, maybe I can jump. One thing let me do. So now that I have this model, I mean, we will get to it. Yeah, so the equations of this model are exactly very, very similar to the Yukawa SYK model. So we're just going to put in indices and average, so I don't even bother showing you how that's done. And then you get these equations for, for exactly the same two graphs that I showed you, this graph and this graph. Except the difference now is a bit more complicated. The self-energies now, the Green's function depend also on space. And in general, or momentum, and in general, the self-energies also do depend on space, although in some limits, the self-energies in them become independent of space, and then you can really solve it without too much difficulty. So, these are all the different graphs, and what you see now is that there are corrections in the self-energy, these two terms that come from this G, and then there are also corrections that come from the spatially random term that are in blue, that comes from V and G prime. Okay, but it's exactly the same set of equations. In the paper with York-Schmalian, this equation as written down has been fully solved numerically, but we can also do a lot analytically. Okay, so that's the technical part of how we're going to get to this. And now I'm going to just concentrate on the physics, on how you derive this model, why it's important. There's a further technical part of solving these equations. Again, I don't know, I can go into some of that in the tutorial, or we'll see. Okay. All right, well, let me now, enough of formalism. Let me just talk about physics now. Okay, so what I'm going to do now is talk about the Hubbard model, but on the square lattice, okay? This is exactly the same as last time for the honeycomb lattice, but now on the square lattice and on a general density, okay? All right.
I'm sorry, Subir, for disturbing again, but
yeah.
you were promising some flavors and some large N, and I didn't see that in the diagrammatics.
Well, just like in SYK, once you average over the flavors, there's no flavors left. Sorry? Oh, okay.
Okay, hold on. So you are telling me that those self-energies are exact because you have taken a large N limit?
Yes.
Okay, I think it's...
That's all. Yeah, exactly. Thank you.
So those self-energies are not approximate, are all the story in N infinite, in NF infinite.
In some fictitious flavor large N limit, which is not written on the board at all.
Because otherwise, right, it's...
Yeah.
Okay, you need other corrections, and we are back 30 years ago.
So the tricky part that took us a while to understand is that some things are random in space, some things are random in flavor, and you have to keep and distinguish the both.
Some things are random in flavor. Which are those?
All couplings.
This looks to me an important step.
But I don't have there is no flavor here.
There is no flavor, in fact.
But once I add the flavor, I make them random in flavor.
But did you add it already?
Huh?
This step is
No,
missing.
I haven't written it out. You can read our paper to see it. It's just
Okay, so I have to believe that those self-energies will be the exact answer in large flavor limit.
large random flavor limit.
Large random flavor limit.
Absolutely, yeah.
And
So, there'll be I, J, L here and I, J, L here, and so on.
And these are flavors.
Yeah, just like in Yukawa SYK. And this will be a random function of these flavors.
And you will justify that, I guess.
Well, that's the limit in which, no, I'm not going to justify.
Okay.
That's the limit in which these equations become exact.
Okay.
So the ultimate test is that this model, without the flavors, you have to study by
Yes.
quantum Monte Carlo.
Yes,
and that has been done, and it works very well. I don't have time to go into that, but there is some new physics at very low temperatures having to do with Griffith's effects and rare region effects, which the large flavor limit does not capture properly. Yeah, well, if I had a few more hours, I'd love to talk about that too. But now let me just talk about we're making these approximations that really appear ridiculous. The only reason we had the courage to make these approximations because we found similar approximation worked really well for the bare Yukawa SYK model. All right. So here's the Hubbard model.
Can I think about it like actually you had the SYK Yukawa one, and then you put it on some two-dimensional space. So
yes, that was one of the dead ends that I didn't talk about. Yeah, I had many papers, and other people also had a lot of papers where they think of each SYK model as some quantum dot, and you make a lattice of quantum dots, and yeah, that doesn't work. It gives you a Fermi liquid at low temperatures. Yeah, we were hoping, okay, maybe it's really low, but there were many other things that were not right. Okay, this one just works. Yeah. Right, so I mean, I guess I'll say, yeah, we were, maybe some of my students, the students who worked on the lattice model, they should be a little annoyed at me because that was kind of a dead end, but it was a very useful dead end because eventually we saw what we had to do. I mean, it's not a dead end, really, we learned a lot, right? That's how things go.
Somehow from the perspective of that you have an exact equations, right?
Yeah.
Somehow, so you say that you have many extra flavors, and then you put a randomness on them, and this already reminds me a little bit of your already SYK.
Yeah, exactly. That's that. Yeah, right. Look, in the end, the SYK equation are very simple. Sigma equals G cubed. I imagine that at various points, many people wrote those equations down. But they never bothered to fully solve them. I mean, certainly it is true that, in fact, these equations, the Yukawa SYK model, which I just wrote down, for the pure Yukawa SYK, they are just the Eliashberg equations. But nobody ever bothered to fully solve them as a self-consistent set of equations. Somehow they didn't. And the fact that they were exact in some limit what gave the inspiration to do all of that. So, okay, so proceeding. I have till 11, is that with some time for questions? Yeah, so let's just take the Hubbard model at any density on the square lattice. All right, so now we're going to do, so first of all, let's just talk about the dispersion. We take free electrons. So in this case, you take first and second neighbor hopping. And if you take first and second neighbor hopping, you get a Fermi surface that looks like this. This is what you see in the cuprates. This is momentum space going from minus pi to pi. And this is the locus of points where you have a Fermi surface, Ek equals 0 on these lines. And this is where there are electrons, and this is where there are empty states, or the holes. And now it's convenient to center this at this point. This point is pi pi. If you center on that point, if you move that point to the center, or as we say, if you move the gamma point to the edge, then you just get almost a circular shape. And why is this better than that? Oh, sorry, why is this better than that? Well, it's easy. But more importantly, if you just look at these shapes, you can think of the system as made up of electrons of a certain density, which is 1 minus p, or you can think of it as made up of holes of density 1 plus p. Which way should I think about it? Well, how do you measure the density of electrons and holes in a metal? You measure by measuring the Hall effect. So when you measure the Hall effect, if there are holes moving, you see the Hall effect. If they're electrons, you have a negative Hall effect. And the do a measurement here of this dispersion, which has been done in great detail. You get a positive Hall effect of size 1 plus p. It tells you there are holes of density 1 plus p. So why does it pick the holes rather than the electrons? That's because the Fermi surface is a simple closed Fermi surface for holes, whereas the Fermi surface for electrons is not a simple closed Fermi surface. That's why this is better than that. It gives you the Hall effect correctly right away. Of course, there's a general, if you take the general formula of the Hall effect, it doesn't matter which one you do, because the general formula Hall effect involves some velocities and so on. It's a little bit more complicated. It'll give you the same answer, though. All right, this has played a role in many things we've done recently, but I'll just mention it. There's something called the Luttinger theorem, that as you put in interactions, as you look at the effect of U, many things can change. The dispersion, the shape of the Fermi surface can change, but what cannot change is the area enclosed by the Fermi surface. That's very robust. It's a topological, it's probably the earliest topological theorem discovered in condensed matter physics. It wasn't recognized topological until work by Oshikawa, but there's an invariant here, which is the area enclosed by the Fermi surface, and that is independent of the interactions, at least as long as you're in this phase with this Fermi surface. Okay. All right, so now we're going to add antiferromagnetism, and here I think I drew it accurately. We're just going to add that, and for graphene it was very simple. You had a Dirac point, and it went from massless Dirac to massive Dirac fermions. So we're going to do the same thing here. But now it's going to be a bit more complicated. There is no Dirac fermion. We'd actually, instead of having a zero energy point, we have a zero energy line or surface. So what happens? So you're going to open up gaps. So in graphene, we knew that once you put this antiferromagnetism, a gap opened up. But since there was only one point where it was gapless, once you open a gap at that point, it's an insulator. But here, you know, this field is going to condense and it's going to open a gap. By the way, this is in graphene, it's very similar to how the Higgs boson gives the fermions a mass. Almost exactly the same thing. The Higgs boson condenses and gives the relativistic fermions a mass. Here, our boson phi is going to condense, and it's going to give the fermions a mass. That's also correct, but only some of them, not all of them. That's the key difference. You can't give a mass to all of them unless you have some very special feature called net, which you don't have in the cuprates. Okay, so what happens? It's just a matter of diagonalizing a 2x2 matrix. So let me do it the way I did it, almost exactly the way I did it for the honeycomb lattice. I write the U as an S squared. I introduce a scalar field J to decouple the S squared. And I take the long wavelength limit of J is equal to phi. Exactly, I mean, this is probably the same slide. No difference. And then I get this theory, again, exactly the same as I would have written down for a graph. There's a scalar field phi, then there's this coupling, Yukawa coupling between the spin density of the electrons and phi. And the only difference, these two both would apply to graphene. The only difference from graphene, this is not a Dirac dispersion. This is just non-relativistic fermions with a Fermi surface. That's the only difference. Okay, so now let's condense phi. Okay, phi as a constant, condense at zero momentum. I mean, the spin density is condensing at momentum pi. K will be pi, but we're going to condense phi at zero momentum because that's the long wavelength field. But we have to keep track of this e to the ik dot r over here. Okay. So this term here, if you write it in momentum space, it looks like this. It's phi q, c dagger k plus q, c. So it's just this term here, you know. It's an electron coming in, and this is phi. There's a sigma here, Pauli matrix, and there's a momentum is conserved, k Q and K plus Q or whatever I choose. That's all. Okay, so now what we're going to do is we're going to say phi of Q is going to acquire an expectation value, phi 0 times delta Q 0. So it's going to just both condense as momentum, which is 0, because the finite momentum has been absorbed. And I'm sorry, I didn't, this wasn't quite right. So what this couples to is the spin density. So if phi carries momentum Q, the spin density carries momentum capital K plus Q. So there should be a capital K here. That's actually crucial. And here capital K is the ordering wave vector, which is pi pi. Okay, so you just condense it, and then you have a very simple electronic Hamiltonian. I guess I can still write it here. Our electronic Hamiltonian is sum on K, epsilon K. I think use C or I use C. C dagger K, sigma, CK sigma. And then I have still sum on K, epsilon. I have phi, there's a phi here. Phi vector, it's coupling to C dagger K, alpha, sigma, alpha beta, CK plus capital K beta. So every time there's a condensate, it adds momentum capital K to an electron. Okay, so if capital K was some arbitrary wave vector, this is quite a complicated thing to do, because what happens, you start with some momentum K, then you scatter off phi, you get momentum K plus capital K. Then you do it again, then you'll get momentum K plus 2K. And in principle, you keep going. But we have the nice feature that 2K is just 0, because it's 2 pi is the same as 0. So in fact, this Hamiltonian is just a 2 by 2 matrix. Okay? So we can write the Hamiltonian as a matrix because it's of this pi feature. So yes, Q equals 0. The condensate is at Q equals 0. I'm just doing a mean field theory here. So the Hamiltonian can be written as something like this, sum on K. It's like C dagger K, C dagger K plus capital K. And then there's a 2 by 2 matrix, and it's CK, CK plus capital K. And this is EK, EK plus capital K. And dropping some indices, there's a phi here and a phi here. That's it. Okay, so that's a 2 by 2 matrix, and you diagonalize the 2 by 2 matrix, and this is the dispersion. Okay, so now we have a more complicated dispersion given by this quadratic formula, and we have to fill, now we have to keep the density of the fermions the same. Now we have to fill all the low energy states up to so that we have exactly the right density. That's what we have to do. Okay, you can ask Mathematica to do that and make some plots. Let me just show you in pictures how we think about this. So we have the original Fermi surface that looks like this. Then you add momentum K. So what you're going to do is take another ghost Fermi surface, if you wish, which is the Fermi surface of these fermions, which are at momentum K. And now what happens is that the phi field couples electrons in the unshifted momenta to those shifted by exactly capital K. So we don't look at all the electrons. Let's just look at all the zero energy electrons. So there were zero energy electrons on this Fermi surface. And when you shift them, those zero energy electrons are on this Fermi surface. Now, in which case is both the original and the final electron on zero energy? In other words, when are both of these 0? Because when both of these 0, then you get a gap. Then your eigenvalue is just plus or minus phi, there's a gap. That's exactly how you get a gap in the Dirac fermion, because in fact, they both vanish at the Dirac point. So which is the point where both of them are 0, which is sort of like a Dirac point, not quite. That happens at 8 points. These are called the hot spots. So at these points, you're going to open up a gap, okay? So if you open up a gap, that means there's no more Fermi surface there. And so now you can just reconnect, and you see you get this. So this is the new Fermi surface. This is the reconstructed Fermi surface that you would get by just putting this formula on your computer. We can just draw a few pictures to show you what that formula tells you. Yeah. No, okay, this is beyond nearest neighbors, because this Fermi surface here, sorry, I didn't mention that. To get this Fermi surface of this shape, you need second neighbor hopping.
Okay.
If you had nearest neighbors, it would be actually just a diamond.
I see.
Yeah, so all of this is for a very realistic thing with first and second neighbor coupling and generic filling, yeah. Okay, well, actually, if you're away from half filling, it doesn't matter. The pictures are pretty much correct. All right, so why are they two different colors? Well, they're different colors because this is a hole. This is where there's no, at this momenta, there's no particles there. And here there's particles. So there's, well, yeah. Anyway, so this is a hole-like Fermi surface, and those are electron-like Fermi surfaces. They're called pockets. And so that's what's happened. You do open up a gap, but you only open up gaps on the hot spots. And then you still have, it's still a metal. So you have a metal-to-metal transition, which is very different from what happened in graphene at half filling. It was a semi-metal to insulated transition. Here you get both are metals, but one metal is less of a metal than the other one. It's a less of a metal because it has rather small Fermi surfaces. It's, this is one picture of the pseudo gap, which is not quite accurate for the Holdorf cuprates, but for materials it would be suitable.
But is the Fermi surface in this transition modifying continuously, or it is a sudden change when you go from one metal to the other? I'm trying to figure out how the transition looks like.
This is the Fermi surface when the gap is 0. When you have a very, very tiny gap, then these are almost touching. So it's a continuous transition. It's just that, right. So there's a sudden jump in the size of the Fermi surface.
Okay.
And they may be in some quantities, but in the sense of free energy or anything else, it's a continuous phase transition. So that was the phase transition that was first studied by Hertz. It's called the Hertz theory. And in the end, all I'm doing here is adding the effect of impurities on Hertz theory in a way we think is the best way to do it. And it took a long time. Hertz proposed his theory in 1976, so it took almost 50 years to understand how to properly analyze the Hertz theory in the presence of spatial disorder. Yeah. Okay. So now as you keep increasing the gap, phi becomes larger and larger, this gap will become bigger and bigger, and several things can happen. So if you start with hole doping, the hole pockets are bigger than the electron pockets, and eventually you just get hole pockets when the antiferromagnetism is large. And this state, you do see at very low doping, in the cuprates, you actually see this. You see these 4 pockets, they have exactly the right volume, and so on. Just very beautiful experiments show these pockets. And beautiful experiments show these too. What's happening at the transition is, of course, where all the fun is. But if you're far from the transition, you see this. Far from the other transition, you see this in a whole host of materials. Okay, so this is the transition I want to now, that's the electron dope case, let's figure that out. Now I want to describe this, the field theory for this. Okay, so this is where, so what we, the vol, yeah, I mean, the volume jumps by 1, because here, yeah, okay, let me just say it. The area enclosed by the holes here is 1 plus P, and the area enclosed by the holes here is P. So so even though it's a continuous transition at this point, when you have both electron and hole pockets, the total area enclosed. So here you would count the area of the hole pocket minus the area of the electron pocket. That's P here, and whereas the area of the hole pocket here is 1 plus P. Yeah. Okay. Yeah, that whole issue of P versus 1 plus P is at the heart of our, our recent thoughts about the cuprates. But the interesting question in the cuprates, that's what made it so fascinating, is that this jump from 1 plus P to P seems to happen without any broken symmetry. And then you definitely require spin liquid physics and some much more subtle phenomena to think about, which maybe towards the end of my question session, if there's time, I can see. That's what we've been working on. For the case of this spin density wave transition, yeah, this is, yeah, if you go through the Luttinger arguments, you can see how this happens. Yeah. I mean, this is all I'm doing is mean field theory, and it gets it right. Other questions? Okay, so I think, so now we have to go through what, okay, so what did Hertz do? Let me just say, what did Hertz do? So Hertz, first of all, he had this theory here, but he didn't have this term here, and he didn't have this term here. So he just took this theory, here, just this part, and he said, well, this I know and love. That's the Wilson-Fisher theory that had not too much earlier, like 5 years earlier, had been fully understood by Wilson and Fisher. This is the Wilson-Fisher theory. And all I'm doing is coupling the Wilson-Fisher theory. Okay, he also had the G, but not the G prime. So he also had this term. Okay, the G is coupling to phi psi dagger psi. There's all these momenta that I've ignored here. So he said, well, let's just get rid of the fermions, because Wilson has taught us that near the critical point, the only thing that matters is the order parameter. Everything else is not irrelevant. Everything else is not important. So the fermions are not breaking any symmetry directly, so let's get rid of them. So he said we just integrate out the fermions, okay? So Hertz said, integrate out fermions. Well, in this case, they're electrons. Okay, so what will you get? Well, at leading order, if this is phi, you'll just get this one self-energy graph from the fermions, phi, okay? So you'll get an additional term, so this thing will become plus, and that term will become, if I write it in frequency space, it'll be phi of k and omega mod squared times chi of k and omega. And this chi of k and omega, actually there's a minus sign because of the fermion loop, anyway. The chi of k and omega is this thing. It's just the fermion bubble. So that's the susceptibility, the spin susceptibility of the fermions at the ordering wave vector, okay? So what we're doing here in terms of this picture, we are near the critical point. Symmetry has not yet broken. We're just thinking about phi on it's about to break. And what we are computing is the susceptibility, the polarizability of the fermions going from one Fermi surface to the other Fermi surface. That's what this bubble is. So this is the vacuum polarization in quantum electrodynamics. It gives you a dielectric constant. This is exactly the thing that gives you a dielectric constant in ordinary theory, except now the dielectric constant is at momentum pi pi. It's not at momentum 0. It's a very large momentum. All right, so this is a standard in every course on solid-state physics, Ashcroft and Mervin. You compute this. It's given by something called the Lindhardt function. In the tutorial, I could go through that if needed. It's one of those things that somebody doing condensed matter will learn, and somebody doing particle physics or cold atom physics will not learn. But everyone should learn it. It's so important. Anyway, so what does this function look like? Well, first of all, it's just a constant. So it's in some sense, it's just a negative shift of the mass. It's making it more likely that the system will order. You can just think of this as just a constant. But what Hertz pointed out is that it has some very interesting frequency dependence. So this is what we call Landau damping. So you take this chi. Yeah, I should have said it's chi of k plus k because of the shift in momentum by k. So if you compute this, and maybe I can get to it in the tutorial, it has this mod omega. Okay, what is this mod omega before you get very scared? First of all, this mod omega is an imaginary frequency. So we are working in imaginary time, and it's mod omega in imaginary time. And what does this correspond to? It's just the oldest term in theory of dynamics. It's what appears in Aristotle, I guess whoever. Before Newton, when there was no inertia, this was the equation of motion of everybody. It's just damping, okay? So what we mean here, think of phi as a harmonic oscillator. You could also add a d tau phi term here. So the action for a Lagrangian for a harmonic oscillator, if you had to ignore momentum, action for a harmonic oscillator is 1/2 d tau phi squared plus some frequency, omega squared phi squared, okay? And now if I write it omega naught squared, if I write it in time space, in imaginary time, this is d omega phi mod squared times omega squared plus omega naught squared. So this is just a world's simplest harmonic oscillator. Okay, but now we get this mod omega term from Hertz. What is our action? So with damping, this is d omega mod phi squared, omega squared plus omega naught squared plus some gamma mod omega. This is mod omega in imaginary frequency. And then what is the equation of motion here? This tells you that, so in real frequency, this is minus I gamma omega is just damping. So if you look at the equation of motion, this term will give you d squared phi dt squared. And this will give you minus gamma d phi dt in real time. In fact, since I'm in Brazil, that's just the Caldera-Leggett term. That is exactly Caldera-Leggett at 0 temperature for an oscillator. Hertz told us you've got to add a Caldera-Leggett term at all momenta in this field theory. Oh, okay, that's all it is. But if you hear this damping term, Caldera-Leggett were looking at the issue of, suppose you had quantum tunneling and you put in a damped harmonic oscillator, would it still tunnel? So here we have not quantum tunneling, we have something like quantum tunneling. We have not just one oscillator, but an infinite number of oscillators, which are starting to condense in a phase transition. And we ask, near that phase transition, if you put in some caldera like the damping to the oscillators, what happens? Yeah, so Hertz had an answer, which was mostly correct, but not entirely. His answer was that completely suppresses, there is no more tunneling, and there's a phase transition where the quantum fluctuations are not that important, and it's almost like a classical thermal phase transition. And that was the conclusion of Hertz's paper. He was thinking mostly in 3 dimensions. Today we know that in 2 dimensions, that's not really correct. There is quite a bit of quantum tunneling, even in the presence of Landau damping. And all of that physics is actually properly captured by these Yukawa SYK equation that I wrote down. Okay. You do at 0 momentum, but now at the finite momentum k, you don't, unless there's some nesting or something. So, yeah, that's another exercise we could go through to actually calculate this and show the mod omega. I will need to look up my notes to do it, but I have them. It's a book. It's all worked out, all the details. Okay. Anyway, so that's that. So this mod omega term that Hertz pointed out, it's correct. It's there, even in 2 dimensions. But there are other effects also that come from the fermion self-energy, which Hertz said, we just ignored the fermion self-energy. We said, there are also terms here from phi. These are ignored. Now, what SYK does is it includes those, because in SYK, these are full Green's functions, where I and Yukawa SYK. That's the important thing. Everything is self-consistent. In Hertz, it's not self-consistent. You just integrate out the free fermions, and you see what the effect of the bosons is. But then you don't worry about how do the bosons back react on the fermions, and then the whole thing has to go in a self-consistent way. And then you also have to include the effects of spatial disorder. So now you see why it took 50 years to understand all of this. At least we claim we understand it now. Maybe we are wrong too. All right, so yeah, so now, this is the phase transition. We're going to look at what happens at finite temperature. So I'll take 10 more minutes to just state the results, and then we'll go to the tutorial session. Yeah, this is the theory. Now I've derived it, where I have both. This is exactly the Hertz theory, without any impurities, and then this has been studied. And what we argued that once you even after you include the corrections from Hertz, it doesn't give you a strange metal. That's a whole another story having to do with the hydrodynamic flow of the quantum critical state. Then we put in spatial disorder, the coupling V that I had here, and we put in this G prime, which I guess I'm calling delta G here. And then from that, we put in flavors. This is the part I didn't talk about. And you look at the saddle point equation, which I already showed you. Now what we have to do is to solve these equations. So one of these equations here, this equation, pi equals g squared gg, that's the Hertz equation. That's the electron polarizability, or the dielectric constant at this wave vector. But we also include this equation, which is the self-consistent normalization of the boson from the fermion. And that's absolutely crucial in Yukawa SYK. That's what we learned. So now we put it here in this more realistic system. And now you solve these equations. Okay, so I'm going to, it can be done, and it wasn't that hard once we decided these were the equation to solve. In the pure limit, these were solved already by Patrick Lee in a slightly different context, and he concluded that in the end, there was a non-Fermi liquid where the self-energy was momentum independent and went omega to the 2/3. That is a correct result. And then they did what we did for graphene. Let me jump ahead. They computed the conductivity. We just did this for graphene, but they did all the correct set of graphs that you have to include at this order. And they said, well, the sigma has a singularity, but my former student, How You Go, showed that they were incorrect. They made a mistake. They didn't properly sum all the graphs correctly, and if you do it correctly, you find it's not a strange metal. All right, so then you go back and you include disorder. Then when you include disorder, you get this omega to the 2/3 becomes a marginal Fermi liquid, exactly what's seen in the experiments. And then you can also compute the conductivity, which we've done here. Sorry, this is pretty quick, but in the end, you get all the things you see in experiments, at least for linear transport. You get linear T-resistivity, but only in this red region as a function of the tuning parameter. This axis here is just this constant S. And here is a Fermi liquid where you have T², and here you have linear T-resistivity. And that's supposed to describe the linear T-resistivity that you see. But what I showed at the very beginning of my talk yesterday was this optical conductivity data for the magnitude and the phase of the optical conductivity, which has omega over T scaling and the scattering rate. And that's exactly what comes out from our calculations as described in this paper. Yeah, okay, I think I'll just stop right there.
Maybe I start with a question myself so people can warm up. Can you go back to the phase diagram of this model? It was very fast.
Yeah, sorry about that. This one, yeah.
No, actually, there was a later one that you were showing with red and blue colors.
This?
I think it's in the PRL by Ilya at the end, the 2024.
Oh, that one, the Yukawa SY came out. Right. So, okay, but that one thing I should emphasize, so in this model, the realistic model, there is definitely a quantum critical point. You have to be at this one point to get all this critical behavior, or in this fan. Whereas in the Ilya model, you didn't have to be anywhere, but that's a zero-dimensional model. If you really had an actual flat band and actual Einstein oscillators, then, yeah, this is the one?
No, I'm sorry, I'm confusing things. Okay, I restate my question. No, this phase diagram, I know it very well.
Okay, great.
So
yeah, you've also worked on this.
I worked on it, exactly. So there's no option that I don't know, right?
Yeah.
No, I'm asking about the phase diagram of the model that you are showing in the whiteboard. You haven't given that phase diagram. This 2D, Yukawa, Hertz theory, however you want to call it.
Well,
and there was a phase diagram when you were flashing through quickly.
This, I think.
It doesn't matter. Can you sketch the phase diagram of this one? Because there was a
It's just this line. So as you tune S, so as you tune the parameter S, at large S you have the Fermi surface and of size 1 plus P. And at small s, you have these holes of size P.
Okay, I can clarify maybe further my confusion.
Here phi is not condensed, and here phi is condensed. And we've been studying what happens near this point. Exactly what we did on the honeycomb lattice, but it's a much more richer story.
Where is the strange metal here?
It's this fan.
It's all strange metal.
Huh?
It's all strange metal, the fan.
It gives you linear resistivity, it gives you 1 over Planckian dynamics, all of that. But to get all of that, this is the most important term that you have to keep.
And that's what I was trying to understand. So how G prime makes emerge the strange metal. So like I wanted to see, I was hoping to see G prime equal to 0, no strange metal. As I increase G prime, I destabilize into strange metal.
Yeah, so that is the story that I went very rapidly.
Yes.
Okay, so let me talk about, that is in fact, that was our revelation.
But sorry, if you go a few slides further, I saw something on that line. Can you just?
Yeah, no, I think let me talk for a few minutes, and then you can ask again. All right. So now let's take the model with both G and G prime and V. Put in disorder. Then we compute the fermion self-energy. So we find, so this first term is just a constant. This is just the Drude term. This is what gives you the Drude theory. The tau in the Drude theory, 1 over tau will be V squared, as you learn. This is the marginal Fermi liquid self-energy. And it comes from two sources. It comes from the G prime, it comes from this, but it also comes from this. Both of them, but both of them give you this omega log omega. So that potentially is what's going to give you linear T resistivity. This G involves the scattering. So if you didn't have, if what V was equal to 0, this thing becomes omega to the 2/3. But once E is non-zero, then this is what, okay? So they both involve disorder, but in different way. This involves potential disorder, this involves interaction disorder. And this is the self-energy, okay. Now let's do transport. Now you have to do these diagrams, okay. Now in the pure case, we found that even though there was something very singular in the self-energy, there was nothing singular in the transport. And this has to do with drag, what's called drag, where you think the electrons are scattering of the bosons, but then the bosons are very strongly coupled and they are scattering the electrons back. There's this whole self-consistency thing you have to account for. And really you should think of it as some fluid that's moving. Now if a fluid that's moving, like water, it obeys hydrodynamics. And the theory of hydrodynamics was written down before we knew that water was made up of molecules. We don't need to know what it's made up of. It's just some fluid that conserves momentum. That's exactly what happens here. You have electrons and bosons interacting so strongly that they just move along together. And just because they're interacting strongly doesn't mean there's any resistance. It's easy to state, but how that emerges from these equations took many years to understand, and prominent people didn't get it right for a while. Now we put in disorder. So now there's something relaxing momentum. This is non-hydrodynamic as far as momentum is concerned. And then you can get a conductivity. So what happens, this is the key thing here. If you now look at the transport relaxation time that appears in the conductivity, this quantity, not in the self-energy, you see there's no G. This is the key point. The self-energy had a G, had a term proportional to G squared and G prime, but it's only this term that appears in the conductivity. G by itself cannot give you a linear T resistivity. So this is linear in omega, wonderful, and if you go to temperature, you get linear in temperature, and you get the whole Planckian thing. For that, you have to solve the full equations numerically, and that's kind of what
there is no G whatsoever in the conductivity. So if I send G prime to 0, I will only depend on V. That's unexpected.
Okay, if you have V equals 0, that is correct. But if you have both G and V, suppose you had...
Exactly. G prime equal to Earth's theory.
Suppose I take this theory with both G and V. Then you can argue that if you did the full theory to higher order, there are some renormalization effects. Once you have spatial disorder in V, you will eventually get, by including some very complicated graphs,
at higher order G prime.
Okay, but we are not including them. We don't know how to include these higher order terms.
Also, they die in large flavor probably for you, right?
That's right. In large flavor, that doesn't happen. But in finite, if you have a small flavor, we expect that V will generate G prime. So we just, since we're doing large flavor, we take a shortcut, and this is, of course, the missing ingredient in the theory, because if you're going to quantitatively compute V and G for any given crystal that some experimentalist friend might give me, we have to be able to do that. We don't know how to do that. So we just, by hand, put in this here for now, and then solve in the large flavor limit. So that's just a trick. We can, of course, numerically do quantum Monte Carlo where G prime equals 0, put G and V, that in principle is sufficient to give you a strange metal, but not in the large flavor limit. Yeah. Okay, so did I answer your question?
No, it's way better now, yes, way better.
Yes.
Thank you.
Yeah.
Thank you. So So you said with this you can capture all the essential features of the phase diagram.
Yeah.
So then what does adding the spin liquid story, like the FL star thing, add to this? Is this just for this?
Okay, so this is for a phase
the
diagram, this phase diagram. Great question. This phase diagram where you have magnetism up to SC and no magnetism here, okay? This is, just by looking at it, this cannot be the phase diagram of the cuprate. It is not the phase diagram of the cuprate. In the cuprate, this SC of this order is way down here. It's like 4% doping. No, not even it's at 4% doping. Whereas the strange metal is more like 18% doping.
So here would the superconducting dome be more on the left? Or?
Yeah, so the cuprate phase diagram, I guess I showed it at some point. I have it here. That's the next part of the talk that so here's the cuprate phase diagram. The strange metal is out here at 20% doping. The magnetism is disappearing. Point, if superconductivity is not appearing, probably some other physics appears here, and in fact it does. There could be that it doesn't apply. It just simply doesn't apply. We need a different theory. But this is for the whole doped cuprates. If you look at the electron doped cuprates, sorry, I don't have the phase diagram. Or if you look at the pnictides, then for those materials, just by looking at it, you can see this is a reasonable phase diagram. So the theory I presented so far in this phase diagram is a theory which I think could apply to the electron-doped cuprates, could apply to the pnictides and many other materials. The one material it could not apply to is the one with the highest DC. So we're very motivated to fix it, because I really don't care about the others. We care about the whole doped material. But let's see, in the tutorial, my plan in the tutorial maybe was to actually just do a tutorial on this theory, the 5-fold field theory, and derive some RG equations. That sounds good. I just actually derive the one-loop Wilson-Fisher equations, from which everything falls. Everything else is, some variation of that. You start from this, then you put in fermions, then you put in Dirac fermions, or you put in Fermi surfaces, you put in disorder. It all starts from Wilson-Fisher, really. At least in my thinking. And so I thought I'd just teach the basics. Then the other basic here is the Hertz result. That has to do with Fermi surfaces. It's a basic property of any metal, is Landau damping. And this is the Hertz is specifically including the Landau damping. And I can also show you how how to compute it. Is that a good plan? Yeah. Okay.
If it's a good plan, only the organizer can say. But I had a question regarding what you said. So I perfectly understand that when G and V are there together, then they will generate G prime eventually. Mm-hmm. But wouldn't be this the same also for the second neighbor hopping? So wouldn't it be true that in presence of interactions mediated by the boson, mediated by whatever, you will eventually renormalize the dispersion relation of the electrons,
yes,
and so curve the Fermi surface? So
yes,
why is it so needed that we have the second neighbor hopping, or you just need it for methodological reason?
No, okay, you're right. Everything you said is completely correct. In practice, what we do is we don't actually solve the Hubbard model when we are applying this to any experiment. We actually take photo emission experiments. They measure the Fermi surface. I just showed a picture of it. So people have done that. So this is experimental data here of the Fermi surface. So people have gone through, they will take this Fermi surface and fit it to first, second, third neighbor hopping. And they come up with numbers. So we just take those numbers. Where it came from, a Hubbard model with our first or second neighbor, we don't know. I should say all people have done density functional calculations. So in this region here, you have the large Fermi surface, the density functional should work. And so people know how there you can start from, the original Schrodinger's equation of the atoms, and do density function and project down to one-band model, and people have done that. And when you do that, you get numbers quite similar to what you see in the experiment. So this is the regime where density functional theory works out here.
And if I may, just another small question. So, but basically all the ingredients were in the paper of 1994 that you were showing. They just didn't get the sum right.
Which paper?
So you showed this paper in which you say that they got this divergence of the Linder function, like 1 over omega to the 2/3 with a coefficient C, and you say that this is vanishing in or it's something more than this, I guess.
So that was a paper with no disorder.
Yeah.
Okay.
Okay.
So this is 0 disorder, perfectly clean. Okay. So they got 2 things. First, they got omega to the 2/3. This is correct. Their calculation, as far as I can see, is perfectly fine, and they've even been numerical tests of it. Then they said, okay, there's such a strong self-energy, this is going to give you some singular transport. So in particular, if they computed the optical conductivity, in Drude theory, this would be 1 over omega squared. They say, oh no, it falls off very, very slowly as omega to the minus 2/3. This 2/3 being closely connected to the self-energy 2/3. They wrote down all the graphs, and then they said, well, they computed the coefficients of these graphs. Where are the graphs? They compute, these are exactly that, this is the graphs they wrote down. They computed all of them, but they said this one, well, this is too much trouble to compute, we won't compute it. So now we have done, Hayu has done that computation. Everything was correct. Everything's correct in the paper. But if you just bother to compute this and add them all up, what they call C is actually 0. So I've asked them, why didn't you compute it? Because C, there are reasons for thinking C is 0. I should say, why I was confident C had to, well, not this particular C, but something closely related, had to be 0. I believed them. But then as I started learning holography and all these other, how you deal with strongly interacting fluids, I started to suspect this result. And now we know it wasn't correct. So they had no reason for suspecting C is 0. And at least in my personal story is, what I learned from holography taught me that C could be 0. And then you go and check it.
So guys, I know there are other questions, but I suggest we ask them Subir in the coffee break because there is the photo now. So I encourage everyone to get out and get the photo. So thanks again, Subir.